All right, 7.0b, review, three-dimensional vocabulary. So we are moving from 2D to 3D for this next section, and this should kind of get us familiar with some 3D objects. All right, so plural for polyhedron is polyhedra. And here are some examples of polyhedra. Let me make sure that top there is showing. These are polyhedra. These are not polyhedra. What do you see might be the condition to be considered a polyhedra? And what makes these not? Anything kind of sticking out for you? Okay, so number one says, what are some differences you notice between the shapes that are polyhedral and those that are not polyhedra? All right, so polyhedra do not have holes and are not made of curved edges. A polyhedron, singular, is formed by joining polygons along their edges. And these are polygonal regions are called faces. Okay, so we need to understand faces, edges, and vertices. Faces are the flat sides. Edges are where the faces intersect, and vertices are the corners. Okay, so on this rectangular prism, you can see that there are 6, 1, 2, 3, 4 around it, and then 2 on the end faces. The edges, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. So make sure that you're counting along 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You're counting all the spots where the faces intersect. Okay, and then the vertices are the corners. So 1, 2, 3, 4, 5, 6, 7, 8. You could also count them like this: 1, 2, 3, 4, 5, 6, 7, 8. All right, right. Regular polyhedron prisms are three-dimensional figures with at minimum 2 parallel polygonal faces of the same size and shape called bases. Remaining lateral faces are rectangles, not necessarily the same as the bases. Note that the base may be any polygon, but the lateral faces are always rectangles. Okay, so this end here and this end here could be any polygon. And then those 2 polygons, those are the bases, they would be connected by rectangles. All right, so we're going to look at complete the following table for the prisms below, counting the number of faces, edges, and vertices. We're going to let F be faces, V be vertices, and E be edges. Okay. All right, so a triangle. Triangular base, that's this thing. Okay, you should see a triangle here and here, and then the triangles are connected by rectangles. Okay, so triangle, I'm going to say n is 3. So triangle, the number of sides on a triangle is 3. Okay, now faces of this thing. We've got 1 on this side, 1 on this side, and 3 rectangles around. So I'm counting 5. 5 faces. Vertices, 1, 2, 3, 4, 5, 6. If we add faces and vertices together, that's 11. And then edges, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, let's do the same thing with this quadrilateral base. Okay, so again, we've got rectangle here, rectangle here. Those are the bases. And then around is the rectangles that are connecting those bases. So the number of sides on a quadrilateral is 4. Okay, faces. So we've got 1, 2, and then we've got 4 rectangles connecting. So that would be 6. Vertices. 1, 2, 3, 4, 5, 6, 7, 8. Add these together. 14. The number of edges. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, pentagon. Okay, so this is a pentagonal, both ways you can say it, prism. So you can see the pentagon on the top and on the bottom, and then rectangles are on the lateral faces connecting those pentagons. Okay, so a pentagon, the number of sides is 5. Okie doke, faces. We've got 5 rectangles, and then we've got a pentagon and a pentagon. So I'm counting 7 faces. Vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of those. Add those together, 17. Edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Did I count that right, or did I miss a couple? Oh, hang on, I think I missed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes, I counted right. Okay, hexagon. Hexagonal, hexagonal means the same thing. Prism. Okay, you've got a hexagon on the top, a hexagon on the bottom. Those are the bases, all connected by rectangles. Okay, so n equals 6, 6 sides on a hexagon. Okay, the number of faces would be 1 hexagon, 2 hexagon, and then 6 rectangles. So that would be 8. The vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Add these together, you get 20. Okay, the number of edges, 6 up here, 6 down here, and then 6 around, so 18. All right, well, what happens if you have an n-gon? Okay, well, let's look at the relationship here. If n is 3 here, you get 5. If n is 4 here, you get 6. If n is 5 here, you get 7. N is 6 here, you get 8. What if n is just n? What happened? How many faces do you have? Hopefully you're noticing that you have 2 more. Okay, if n is 3, the vertices is 6. If n is 4, the vertices is 8. If n is 5, the vertices is 10. If n is 6, the vertices are 12. Okay, what's going on with every one of those? They're doubling, so we better double n, 2n. Okay, now if we added these together to get this, added these together to get this, what happens if we add these two together? Do you see 3n plus 2? And now for the edges, 3 and 9, how are they related? 4 and 12, how are they related? 5 and 15, 6 and 18. I'm seeing that those are multiples of 3. So there's your little formula if you have an n-gon. That will always work for the number of edges. All right, complete the following table for the pyramids. Okay, these were all prisms. Okay, prisms have 2 bases that are polygons, that are connected by rectangles. The lateral faces are rectangles. Pyramids have some sort of a polygonal base, some sort of a polygon that's on the bottom, and then triangles connect to form, to meet all at the same, it's called an apex up at the top. Okay, so let's do the same thing on this. So again, a triangle has 3 sides, quad has 4 sides, pent 5 sides, hex is 6 sides, and then finally, what is it with an end on? All right, triangular pyramid. Triangular pyramid has 4 faces. It has the bottom triangle, and then it's got 3 triangles coming up to an apex. Vertices, 1, 2, 3, 4. Add those together. Edges, 1, 2, 3, 4, 5, 6. Quadrilateral, this guy right here, it's got a rectangle on the bottom or a square if they're the same size. Okay, and then you've got 4 more triangles going around meeting up at an apex. So that would give us 5 faces. Vertices, 1, 2, 3, 4, 5. Add these together. 10. Edges, 1, 2, 3, 4, 5, 6, 7, 8. Pentagon on the bottom, that's the base. Going up to a pyramid here, an apex. Okay, so we've got 1 pentagon on the bottom with 5 triangles around it, so that's a 6 faced figure. The vertices are going to be 1, 2, 3, 4, 5, 6. Add those together. The number of edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hopefully you're starting to see a pattern here. Hexagonal. Hexagon on the bottom, triangles connected to all those edges coming up to an apex here to form a pyramid. So that would be 7 faces, 7 vertices, 14 when you add, and the number of edges is going to be 12. Okay, now if you have an n-gon, what is going on with 3 to 4, 4 to 5, 5 to 6, 6 to 7? N plus 1. Same thing here, n plus 1. Faces plus vertices, if you add these together, don't you have 2n plus 2? 3 to 6, 4 to 8, 5 to 10, 6 to 12, n times 2. 2n is the formula to find the number of edges in a pyramid. Okay, Leonhard Euler was a famous Swiss mathematician that lived from 1707 to 1783. Euler is credited for the use of the symbol pi. His contributions to geometry include finding the relationship between F, V, and E for all polyhedra. Look at the tables above and identify the relationship with these 3 variables. All right, so we've looked at the relationship this way, and this way. But what about between the F plus V and the E? The F plus V and the E, the F plus V and the E. Doesn't it make sense that the faces plus the vertices, this guy, is this plus 2? Is E plus 2. Let's see if that makes sense up here. This equals this plus 2. Okay, so that's the relationship. Okay, everywhere else is different. This is different. Whoops, too far up. This is different than this between prisms and pyramids. But the relationship between these and these can be noted. Okay, so that's your relationship. Thanks, guys.